right, so in 8.2 and 8.3, we are going to now construct and interpret confidence intervals. Okay? Today we're going to talk about at least how do we go about interpreting our results when we actually get a confidence interval. What does it actually mean and how do we state it? Okay? And then we're going to talk about some of the pieces and some of the things you need to do when constructing a confidence interval. Tomorrow in 8.3, what we'll do is we'll put it all together and we'll show you the 4-step process when doing any type of confidence interval. So the first thing that we want to talk about today is really the interpretations. When interpreting a confidence interval, sometimes you'll be asked to either interpret the confidence level, okay? So when we talk about confidence level, as it says up here, if I want to do, for instance, if I'm saying a 95% confidence interval, all right? What does that level actually mean? Okay? So when we start to interpret it, we'll want to write it in this type of context. Basically what we're saying is that 95% or whatever percentage it is of all possible samples of that same size from this particular population is going to capture or get our unknown parameter that we're trying to find. So when we're talking about this unknown parameter, we'll actually want to put it in the actual context of what the parameter we're actually trying to find. You can also be asked to calculate out or to state what the actual confidence interval means. So when we're talking about a confidence interval, and I like to, or when I interpret them, I like to kind of use a fill-in-the-blank sentence. I've given it to you here, okay? So how I like to phrase my confidence intervals is something to the extent of, we are blank percent, and I apologize there's not a percent there, or a blank there, but it says C percent, but blank percent. It might be 90, it might be 85, whatever the percentage, so we'll say we're 95% confident that the interval from, so when you actually find your confidence interval, you'll state the lower bound. So this is your lower bound to your upper bound. And then we'll say that it actually captures the actual value of the whatever we're trying to find. So down below here we have some examples that will show you how we go about interpreting the confidence interval and the confidence level. So the first example here, I'm just going to slide this up a little bit so you can see it. Says, according to a Gallup poll, www.gallup.com, on August 13th in 2010, the 95% confidence interval for the true proportion of Americans who approved of the job Barack Obama was doing as president was 0.44 plus or minus 0.03. Interpret the confidence interval and the confidence level. So if I'm thinking about this value, 0.44 plus or minus 0.3, well, if I subtract it, the lower bound of my interval is 0.41. If I add that, my upper bound is 0.47. My percentage of confidence is 95. So I can go ahead and start filling in this sentence. So I would say we are 95% confident that the interval from 0.41 to 0.47, okay, captures the true proportion of Americans who approve the job Barack Obama is doing as president. So I have that basically summarized right here. So again, we are, that's the blank, 95% confident that the interval from lower bound, upper bound, captures the true, and then I write what I'm actually, the parameter that I'm finding in the context of the problem. The true, and it's coming right here, the true proportion of Americans who approved the job Barack Obama was doing as president.
Could you say the true value of?
I suppose you could say the true value, sure. Well, I would rather have you say proportion because that's what it actually represents. Because you'll want to either say proportion or later on we would say mean or what it actually specifically represents. Value is a little too vague. Because we want to know, are we talking about a proportion? Are we talking about a mean, a standard deviation, a range, interquartile range, third quartile? So now, what does the level mean? Okay? So when we talk about the level here, okay, so we're talking about basically 95% of all possible samples of the same sample size from our population is basically going to give this interval of the percentage of people or the proportion of people who think the president's doing a good job. So 95%, again, of all possible samples of the same size, the resulting confidence interval is going to capture the true proportion of Americans who approve the job the president is doing, or the job Barack Obama was doing as president. So again, our whole idea of confidence intervals and this confidence level is basically telling you, if I do this process over and over and over again, that percentage of confidence intervals is going to capture the true parameter. So our true proportion in this particular case. So what I'd like you to do is, I'll read number 2 with you, but I'd like you to find the confidence interval and the confidence level. So in number 2 it says, how much does the fat content in brand X hot dogs vary? To find out, researchers measured the fat content in grams of a random sample of 10 brand X hot dogs. A 95% confidence interval for the population standard deviation is 2.84 to 7.55. That's a lot of variability there. Okay, so take a minute. All right, so here is what I wrote. Does your answer have to be word for word like this? No, but hopefully it's relatively close. So interpreting our confidence interval, we would be saying we're 95% confident that the interval between 2.84 and 7.55 grams captures, oops, I forgot the T in captures, I don't know if any of you noticed that, the true standard deviation of fat content of brand X hot dogs. Notice how the parameter in this case is not a mean or a a mean or a proportion, but it's actually a standard deviation. So the interpretation of the confidence level, basically what we're saying is, if in 95% of all possible samples of 10 brand X hot dogs, what's nice about this is we know what the sample size was, so we can actually state that here. The resulting confidence interval will actually capture our true standard deviation. So 95% of all of our confidence intervals of basically size 10 hot dogs, okay, is going to actually capture our true standard deviation. So, now, this is a very interesting question, part C, and I like putting this on here because we want to make sure that we understand how, or the correct interpretation of confidence intervals. So in this particular question, true or false? The interval 2.84 to 7.55 has a 95% chance of containing the actual population standard deviation. Is that true or false? How many of you think it's true? Not a single hand up. How many of you think it's false? Ooh, maybe. Okay, I have one, two. Why do you think it's false? Since I actually got a couple hands. Right? Well, this interval is based on how many samples? Okay, that's the sample size. 10 is the sample size. So this interval is coming from how many samples?
You don't know.
Just one. One sample of size 10. Okay? So, when we talk about 95% chance, the 95% talks about how many intervals in the long run are going to capture the true mean. Not that this particular one has a 95% chance. In fact, what's the possible probabilities that this interval captures the true mean? Give you a hint, it's only one of two answers. Right? What's the probability if the mean is actually in there? If it actually captured it, what's our probability? Say that out loud. No, I heard someone say, I thought I heard someone say the exact answer. If it's in here, what's the probability that it got it? 100%. Okay? If it's not in here, what's the probability? 0. Okay? So this is false. Your probability is either going to be 1 or 0. Either the interval actually captured it or it didn't. Because if I do another confidence interval, I'm not going to, or if I do another sample, I'm not necessarily going to get this exact interval. I might get something different. But if I look at all of my intervals, 95% of those should have the true population standard deviation. But when we look at one, either it captures it or it doesn't. It's one or the other. All right, one page down. Let's move on to the second page. So how do we actually construct our confidence interval? Constructing your confidence interval will depend on a few things. The first thing that it's going to depend on is what parameter you're trying to construct the interval for. However, what's really nice about confidence intervals, they have the same kind of basic structure. Okay? And the structure goes like this. You're going to have a statistic. Okay? In our course and in our class, we're going to focus on two types of statistics. We're going to focus on a sample mean, x bar, or a sample proportion, p hat. Then we're going to have our critical value. This critical value will depend on the size of the confidence interval. I'm going to abbreviate that CI. Because as we saw a little bit yesterday, if I go 68% versus 95% versus 99%, the interval gets bigger as the percentage you want gets bigger. So this critical value will help determine that. Then you'll multiply that by the standard deviation of your statistic. Okay? So when we're talking about this standard deviation, if we talk about it when we talk about a proportion, if we remember back in chapter 7, for a proportion, the standard deviation is just p times 1 minus p over n square root. But if we're talking about a mean, we're going to be talking about a standard deviation over the square root of n. So it depends on if we're talking about a mean or a proportion. Now, getting back to this critical value, since it depends on the size of the confidence interval, this critical value for some of our confidence intervals, and for all of them for right now, really acts as a z-score. It basically tells you how many standard deviations do you want to be away from your parameter of interest. So to find this critical value, and this sometimes is a challenge, right, for some, we have some practice examples on how we go about finding our z-star scores. And you'll see that it's plus minus because you go to the left and to the right. So for this first example, okay, it says find a z-star score for a 90% confidence interval using table A and your calculator. I'm going to show you both ways of doing it. So, where the z-score is coming from. Draw a picture of your normal curve. We're going to assume our distribution is normal. And that's something we're going to talk about on the next page. If it's normal, okay, and here's my parameter of interest, say it's a mean, or it's a sample, or it's a population proportion. Let's just keep it as population proportion, because I know that's what we're going to go to next. What I want to do is I want to figure out where are 90% of these values located. So I'm looking at, where is this z-star located? So, one of the ways I can do this is by looking at a table. If I'm looking at table A, take a second right now, go through your notebook and see if you can find your pink sheet, table A. Okay.
What was that last term?
That was chapter 2. The nice thing is, your book has a table A in it. So if the table A method doesn't work, then it will be helpful for you to learn the calculator method.
So us finding this z-star right here,
Well, it's going to be part of it. Yes, it's going to make up the margin of error. Okay? So, if I'm looking at it at a table A, and I'm going to use table A, the first thing I need to do is figure out how much is this area right here. It's 5%. How'd you get 5%? You're right.
Because 100%, there's 90, and then there's 10% left, so you have to split that up.
So it's 10% left,
Yeah.
it's symmetric, so if I divide that in half, I have 5% left and 5% left. So on table A, what I'm going to do is I'm going to look at areas of 0.05 and 0.95 and look at what z-score corresponds to that. So if I'm looking at the 0.05, and I'm going to go to my table A here. I think I have my table A marked right here. So if I look at table A, I'm looking at, and again, these are all of my areas. I'm looking at an area that's closest to 0.05. So I start to scan here, 0.0446, 3, 5, so it's somewhere in here. If I look right here, here's 0.0505 and 0.0495. Which one's closer? Aren't they equal distance away? Okay, so if I look at the z-score, it's negative 1.6, and then if I go up, it's either 0.4 or 5. I would accept either one. All right, here, let me get to the right page here. So my z-score for this one would be negative 1.64 or negative 1.65. I would accept either one from the table. Now here's the nice thing. What's going to be true about 0.95? It's just the positive one. So you really don't have to do it twice. Now, if you don't like to use the table, you can use your calculator. To use your calculator, we use the function inverse norm. You do inverse norm of the percentage, that gives you your z-score. So, in our case, I could go inverse norm of 0.05 and inverse norm of 0.95. Might have to warm up my calculator here. So I just shut down my computer during second block's lecture, which was not fun. All right. Oh, it still has the old stuff from yesterday. So, inverse norm, second vars, number 3. So this is going back to chapter 2 stuff. Inverse norm, 0.05. If I hit enter, look at that, negative 1.64. Heck, if I rounded it, it'd be to 3 decimals, 5. So we would get negative 1.64. If we do the other one, I bet it's 1.64. Just to show you, second vars, number 3, 0.95. Look at that, 1.64. We got our critical value. This is telling us how many standard deviations I have to go to the left and to the right to create my confidence interval. All right, let's try the second one. Z-score for a 95% confidence interval. All right, so 95. So what's my area here?
0.25.
Okay. Well, it's 2.5%. Yeah. Because half of 5% is 2.5%. So if I go just to the calculator, inverse norm, since most of you have calculators and only a few have your tables, if I wanted to find the first one, what would the value I put in my calculator be? 0.025. Because 0.25 is actually 25%. And then this one would be 0.975. because it's the 2.5% plus the 95%. So, on my calculator, second var is number 3. Inverse norma, 0.025. Negative 1.9599, so could we say negative 1.96? Guess what the other one will be? Positive 1.96. Now, anybody in here go, 95%. What other number would have been at least acceptable that we could have potentially used? 68, 95, 99.7 rule. 95 would be what? How many standard deviations away? 2. Notice how this gives you a more exact answer? Okay? So from now on, we actually, since we have the technology, we'd rather not use the estimate 68, 99, or 95, 99.7 unless we have to. So 95%, negative, and positive 1.96. All right, take a minute and try C and D. 80% confidence interval, 75% confidence interval. No one there.
So we just found the
We just found what's called the Z-score. Basically, how many standard deviations do we want to be?
Do I have to do this thing?
Correct. One is the lower bound, one's the left side, and the other is the right side. Yep. Basically, what's happening is the reason why you found 2 of them is the negative's going to give you the lower bound confidence interval once we eventually calculate that, and the positive Z-score will give you the upper bound.
eventually, but these aren't the concrete.
What we would do is we're going to take those numbers. I would have to give you up here what the sample proportion is. So, like for instance, say if in the President Obama one, his sample statistic was 0.44. Okay, say if our critical value is this 1.96. Okay, we'd have to calculate out the standard deviation, whatever that value was. So say it was 0.44 times 0.46 divided by whatever the sample size was. I don't know what the sample size was, but I'm just going to write n there. And that would give us our lower and upper bound, and it would give us our confidence interval.
So before we were doing finding the Z-score, they already something else to answer the question, right? But now we're finding the Z-score to find the upper numbers.
Right, in order to find the actual confidence interval, you have to calculate out the Z-score to get this critical value. The critical value is going to tell you how many standard deviations you have to go below and above to capture that percentage of the interval. Okay.
So for this, it's not like the next one is, we didn't calculate.
Wait, Mr. Barnes.
Alright, take a look and see how you guys did on the bottom 2. Okay. So on the 80% confidence interval, as you can see, I drew the picture here. 80%'s in the middle, leaving me 20%, so 10% on each side. So inverse norm of either 0.1 or 0.9 will give me the negative and positive Z-score. So negative 1.28 and positive 1.28. For 75%, that leaves you 25%. So when I divide 25% in half, I get 12 and a half and 12 and a half. So inverse norm of 0.125 or inverse norm of 0.875 gives me a Z-score of negative 1.15 or 1.15. So basically what's happening here is you're figuring out how many standard deviations away from the mean do I need to go. In essence, how far do I need to go to the left and to the right to help me calculate out my lower bound and my upper bound of my confidence interval. So one of the things we will do tomorrow is actually do these calculations, okay, and do the interpretations which we've talked about. But there's one last thing we actually have to do with confidence intervals, okay? And that is we have to check and make sure certain conditions are met when doing, okay, confidence intervals. Because we've made some assumptions when doing these calculations,
Like that's normal.
okay? That's one of them. You are correct. So, on the next page, conditions for constructing confidence intervals. Okay? When you construct a confidence interval, you have to demonstrate and show 3 things, okay, have been met before you actually calculate it out. Okay? So when we do that 4-step process, these conditions, checking these conditions, okay, is part of the second step. It's part of the plan. Okay? So, the 3 conditions are the following. First of all, the data that you collect must come from a random sample. Okay? It's usually pretty easy in a problem. I'll say, hey, we collected a simple random sample. Beautiful. We're just going to state, hey, we got a simple random sample. We saw back in chapter 4 that bias can occur if you don't do random sampling. You'll get biased results. So if we're getting biased results, our confidence interval is not going to be very accurate. The second one, normal. Our sampling distribution of our statistic has to be normal. Okay? So this becomes a little more fun because it depends on the statistic. If you're talking about a sample proportion or a sampling distribution of a sample proportion, those conditions are where we show that n times p and n times 1 minus p are both greater than or equal to 10. However, if we're talking about a sample mean, okay, there's many things you got to check. If the population distribution is normal, then the sampling distribution is normal, or if n is greater than or equal to 30, if your sample size is greater than or equal to 30, central limit theorem. So some of those things we learned back in chapter 7 come back into play here. Then the last part is independent. Each observation must be independent, meaning one doesn't impact the other. In the independence, you also should show that the population is greater than or equal to 10 times your sample, especially when you're sampling without replacement, so that the standard deviation can be used. So to demonstrate these, let's check or go through the first example together. So, it says check whether each of the conditions is met for calculating a confidence interval for the population proportion P. So we know it's going to be a proportion. That's nice. So, in A it says, Glenn wonders what proportion of students at his high school think that tuition is too high. He interviews a simple random sample of 50 of the 2,400 students at his college. 38 of those interviewed think tuition is too high. Okay? So the first thing I want to check is it random? Is this condition met? Yeah. What did he collect? Yes. Glenn took a simple random sample of 50 students at his school. Excuse me. Next question is it normal? Why? That is the wrong condition. It's not a mean. So central limit theorem doesn't save you here. What do you actually have to check? Not the 10% rule, is n times, in this case, p hat, 10, and n times 1 minus, so you can think about it this way. N times p hat is the number of people that say yes. N times 1 minus p hat is the number of people that say no. So in our sample, how many people said yes? So this number here is 38. Because it would technically be n is 50, p hat is 38 out of 50. So when I multiply those, the 50s would cross out, leaving me just 38. So 38 said yes. How many said no? 12. There's a total of 50 and 38 said yes. That leaves 12 saying no. Both of these are greater than or equal to 10. Barely, but it's still good to go. Independent. So, one student's answer, or student's response, does not influence another student's response, and is the population greater than or equal to 10 times our sample? Well, what was our sample size? 50. So what's 10 times 50? 500. Is our population of our school greater than 500? Yes. 2,400 students in the school. So this is a yes. All three conditions are met. Is that me or someone else's secret? Could be me. All right, I want you to try B. All right, as you check up here, I put up the solutions real quick here. On part B, okay, is it random? Yes. You took a simple random sample of 120 pennies. And yes, you need to be specific about saying what the random sample represents. I know some students will just say random, yes. Well, what did you actually take a simple random sample of? You need to be specific with that. Is it normal? In our case it is, because I'm checking to make sure the number of successes and the number of failures I get are both greater than or equal to 10. In our case, we had 57 pennies that actually were more than 10 years old. Okay. So we had 57 successes, meaning we had then 63 pennies that weren't, because these two numbers should add up to your sample size. If you prefer using the formula, again, your sample size was 120, okay? your sample proportion is 57 out of 120. So you can plug those values right here. The 120s would cancel out, giving you your 57. On this one, when you go 1 minus 57 over 120, it'd leave you 63 over 120. Hence then when you multiply it by 120, you're just left with the 63. The last part, the independence, we're sampling without replacement. So we're actually taking the penny out, we're not putting it back in, we're just taking out 120 pennies. So we want to make sure our population is greater than 10 times our sample. So our population in this case, or I should say our sample was 120. So we got to make sure we have at least 1,200 pennies in our jar. The nice thing is they told us that our jar contained at least $20. So we know our jar has over 2,000 pennies in it. 100 pennies in a dollar, at least $20 is 2,000 pennies. So this condition is met.
Will it always give like the $20 in pennies?
Will it always give you the population, give you an exact number? Not necessarily. Sometimes what they'll say is, they might give you a problem, they'll say, in a large city. Well, if we were talking about large cities, we're talking about probably several 100,000 people. They might say in the United States. Well, now we're talking 300 million people. Or they might say adults in the United States. Okay, now we're talking adults, okay, 240 million
So is
people.
that what you would write?
Okay. I would just say it's safe to, it'd be like how we'd say it's safe to assume there are at least, 1,200, if these were people in the United States, I'd say it's safe to assume there's at least 1,200 people in the United States. Right? We know that there's over 300 million people. So it all depends on the population. Sometimes they give you the exact numbers. Sometimes you have to kind of make some assumptions, but usually they seem to be realistic because they'll set the population, it might say at a large school district, or they'll make sure that that population is met. All right, with that being said,